bioinorganic events here. We're going to be here for 11 days. We already have the first of 12 nights behind us. May I ask, did anything happen yesterday after 10:30 in downtown? Who was out in downtown after 10:30? Okay. Well, okay. I see two hands, and I know who these people are. And I have actually, yes. So I think the Penn State party coordinators need to up their game. And I think we want to have a shout out to the University of Washington and to the University of Michigan. And I think Audra may want to help out, and Ellen, so they know what to do. Well, we start off with a series of, but in all seriousness, where we're going to meet tonight has already been announced. And so now let's come to the day. During the daytime we do science, and we are very fortunate to have Frank Neese here. He's giving 2 talks today to set the pace for coordination chemistry and quantum chemistry. And these are very important, very nice introductions to the field. And without further ado, I'll hand over the mic to Frank. The way we had that the last time, if you have questions, make sure that you ask your questions. We have it usually that it's listed for 90 minutes because Frank goes twice in a row. If he needs a break, then we just do a quick break. If you have a question, ask your question. It should be interactive. Okay? Frank?
Yes, good morning, everybody. It's a great pleasure to be back here at Penn State and at that workshop. So I think it's already the 3rd time, and I'm very happy to be back here. So I guess this morning you have the choice between bad and worse, by either being out there in the rain or being inside here stuck with a babbling theoretician. And so I try to defend my presence here and tell you why it is useful to worry a bit about theory. So many of you will be involved in like isolating proteins or doing spectroscopic experiments. And then ultimately you will want to ask yourself, what does it all mean? So why did my advisor tell me to do all that stuff that he made me do? And now I have some wiggly line on paper, and I want to make sense out of it. And I want to make sense out of it in terms of like the structure of the active site that I'm studying, or the reaction mechanism, or even the electronic structure. And very often you will find yourself being redirected to a paper, say a paper by, say, Ed Solomon or Thomas Brunold or some other spectroscopist, and you think, damn, these people are talking Chinese there. And then so it was like one of my very early encounters with Karsten was when I met him at a bar, I think in like some after conference social event, and he told me, you know, Frank, that is after a long day in the lab and I really can't sleep, that's when I read your papers. So I guess my job this morning is to try to demystify a bit of like that language that is being used in these papers. And so we start off with ligand field theory, which is the language of coordination chemistry. And the first thing that I want to do is to put that into perspective by taking a bird's eye view on what theoretical chemistry is. And I think it is very important to get that clear in your mind of what we want to do with ligand field theory. So quantum chemistry is firmly based on quantum mechanics. So deep down, quantum mechanics is the physical theory that describes matter. And it describes matter to the best of our knowledge perfectly. So that means if we apply the rules of quantum mechanics perfectly and without making any approximations, you get numbers that are as good as you can measure them and better, meaning that if you improve your experiment, you will find the numbers that quantum mechanics is predicting. And that would be happening if you would solve the molecular relativistic Schrödinger equation exactly. So that is a marriage between quantum mechanics and the theory of relativity. Now, that is not possible to do exactly, and so there is a series of approximations here, and in the second lecture I will try to to gently walk you through that series of approximations so that you can at least catch a gist of what it's all about. And that would lead you to computational methods. And these computational methods, they produce numbers. And for each and every molecule, they produce a given number. And that's it. So say the total energy of that molecule. Now, it does not talk to you about chemistry at all. So it simply gives you the numbers saying, this is my structure, this is my energy, end of the question, that's all I'm going to tell you. But if you like chemistry, that's not good enough for you because you want to know more. You want to have a pictorial understanding, and you want to understand what is characteristic for that molecule in the context of the class of substances that you're studying. And so in that sense, you don't only want to have a theory of individual molecules, which is what quantum mechanics ultimately is, but you want to have a theory that is talking about a class of substances, and thereby creating a language. And that leads you to phenomenological models. And ligand field theory is one of those phenomenological models. The other one that you are certainly aware of would be the Huckel theory of aromatic compounds. And of course, in your courses of organic chemistry, it's unthinkable to teach such a course without making recourse to the concept of aromaticity and pi systems. Quantum mechanics doesn't know anything about that. It comes about by putting a pair of goggles on and creating a language. And that language is the cornerstone of having phenomenological models. Yeah? And that allows you to create a language with which you can talk about observable facts. And these observable facts are the things you measure in your experiments. Yeah, so to summarize that, ligand field theory is a semi-empirical theory that applies to an entire class of substances, namely transition metal complexes. It thereby creates a language with which you can cover a vast number of experimental facts. Yeah? So it is absolutely fantastic. And as we all know, the chemistry of the transition metals is quite a bit more complex than the chemistry of the main group elements. And without ligand field theory, I think it would be very difficult to find a pathway through the jungle of complexity that is presented to you by the experiments. But you will also see that ligand field theory is a model, and the very nature of a model is that it applies to only a restricted part of reality. It doesn't want to cover all of the world. It covers a very well-defined, restricted part of the world. Yeah? So in terms of theoretical language, ligand field theory creates an effective Hamiltonian that only carves out, that puts a spotlight on certain aspects of the electronic and the geometric structures of transition metal compounds, but it's not all comprehensive. Now, ligand field theory is not an ab initio theory that lets you predict properties of a compound from scratch. So you cannot draw down a compound, and then you can ask at which precise G value will it resonate in my EPR spectrometer. Ligand field theory will not tell you that. It will tell you what the general shape of the spectrum you can expect to get, but it will not tell you precise numbers. And what it's also not, ligand field theory is not a physically concise and rigorous treatment of transition metal electronic structure. In fact, if you take ligand field theory serious and really calculate everything the way that ligand field theory writes it down, you end up with absolutely ridiculous numbers. Yeah? So it is deliberately wrong. It's a characteristic of a scientific model that it's deliberately wrong in the interest of making an abstract statement that guides you through experimental facts. It's a little bit, it sounds a bit self-contradictory, but it's very worthwhile, spending some time and a beer or two to think about what that really means. So now let's dive into that, and coordination chemistry, and of course that is what ligand field theory is talking about, is built around the transition metals. And now here is my chart of the periodic table. Until very recently, I think I would have been hard-pressed to name any additional element on top of that. But yeah, you know. And it's, but these are these are just a part of the periodic table that's biologically relevant. And so we are zooming in here now on the transition metal series. And of the transition metal series, it's basically 7 out of 10 are biologically relevant. So there is no known role of scandium, titanium, or chromium. And of the second and third row, you will find molybdenum and tungsten in biology. And these are the main transition metals that play a role here. Now, I think you all in your general chemistry have learned about the chemistry here of the first row elements, main group, and like how they bond and how they react and so on and so forth. Now, the transition metals are different. And what's different in the transition metal is that you have the 3D orbitals here in the first transition row that are partially occupied. So as each orbital can be occupied by up to 2 electrons, that means the D shell covers up to 10 electrons. Now, and it's the chemistry of these electrons in those d orbitals that give like all of the complexity, but also so many of the wonderful features of transition metal chemistry. So when we start to explore that, I want to make 2 more introductory statements before really diving into ligand field theory. And the reason for that is that chemical textbooks are guilty of many conceptual crimes. And I wanted to clarify a few things here. Now, in this world, atoms, molecules exist in states. Atoms and molecules are many particle objects, so they contain many electrons. And these many electrons arrange themselves to give discrete states. Now, in this world, every experiment and any experiment always are observing these possible many particle states of the system. Yeah? So a quantum object of many particles can exist in various states. These are the electronic ground state, various excited states. And the spectrometer probes transitions between these states. Now, if any one of you thinks about orbitals at that point, you're wrong. There is no such thing. We will later introduce orbitals, we will use orbitals, we will look at orbitals, we will like orbitals, we will do all kinds of things with orbitals, but orbitals are not observables. Orbitals are not fundamental to nature. They don't exist. They're auxiliary quantities that help us to think about the problem. They're extremely useful to build up computational approximations, but there is absolutely nothing fundamental in orbitals. It is the state that matters, the state and only the state. Everybody who tells you something different is fundamentally and conceptually wrong. Sorry. You know, I once had a math teacher, and the math teacher was saying, you know, I really like discussion. I'm like crazy for discussion. But, you know, sometimes there is only one right thing, which happens to be what I'm saying. In this case, I'm really sorry, but that's the way it is. Yeah, that is. So, it's a very strong statement because, and if you like take that into your heart, I promise, you never make a mistake if you start thinking from states. But you can make fantastic, terrible mistakes if you like mix orbitals and states without really knowing what you're doing. So, like, what is the way to a state of an atom or molecule? So first of all, so you have a bunch of electrons, and the bunch of electrons is distributing among the available orbitals of the system. And so that defines an electronic configuration. It's simply a set of occupation numbers that tells you, like, which orbital is, say, doubly occupied, singly occupied, or unoccupied. Now, if there is any symmetry, spatial symmetry in the system, then that configuration leads to a given states of a given symmetry. It's usually denoted by a quantum number, capital gamma. Now, if you have unpaired electrons in the system, they will rearrange themselves to a given total spin. And that is a total spin quantum number S. And that total spin will have one more degrees of freedom associated with it, which is a projection of the spin onto the z-axis. So if you had your introductory quantum mechanics, that is so-called m sub s quantum number. And so for a given total spin s, there are two s plus 1 magnetic sublevels, as we say. M sub s equals s, s minus 1, all the way down to minus s. So if you want to have a notation for such a state, then you would have an occupation number vector n, a given total spin arising from a given spin coupling k, a projection quantum number m, and then you would have spatial symmetry labels gamma. Now, let's dwell a little bit on the total spin, because here's also where many people get very confused, and I think it's important to get that down. It is not a shame to be confused after that slide, because the subject is somewhat complicated, and if you really want to get down to the bottom of it, you will need to spend some more time than we can do here in the lecture. Now, what is the total spin? So first of all, if you have two electrons in doubly occupied orbitals, they do not contribute to the total spin because they couple to a singlet, and that is s equals 0. Now, singly occupied orbitals can be either occupied with a spin up or a spin down. And all of these electrons that are in singly occupied orbitals, they can be coupled parallel or anti-parallel to produce a final total spin. Yeah? And as I said, for a state with total spin s, there are two s plus 1 components that we call magnetic sublevels that vary from m equals s, s minus 1 down to minus s. Now, the thing is that you should make a proper distinction between the m sub s quantum number and the s quantum number. Now, the m sub s quantum number is just the sum of the individual m sub s quantum numbers. So notice that, like with lowercase symbols, I talk about one electron quantities, and with uppercase symbols, I talk about many electron quantities. Now, this example here is easy. You have two doubly occupied orbitals. They do not contribute to the total spin. One singly occupied orbital. So we got to have a total s of s equals 1/2. And if that spin is up, the m sub s is also 1/2. Now, in this example here, we have two unpaired electrons. And in that case, the m sub s is 1/2 plus 1/2 equals m sub s equals 1. And in that case, also the total s equals 1, because there is only one way to do that. However, if you now have, say, here 3 unpaired electrons, now this arrangement of spins does not correspond to a given total s, but to a given total m sub s. So the total m sub s is 1/2, minus 1/2 is 0, plus 1/2 is 1/2. So the total m sub s is 1/2. However, this arrangement here contributes to two different spin states. It does contribute to the m sub s equals 1/2 component of an s equals 3/2 state, and to the m sub s equals 1/2 component of an s equals 1/2 state. Now, if you really wanted to construct the true s equals 1/2 and s equals 3/2 state, we would have to do a little bit of math, and we would need more than one such picture. That is the art and science of constructing so-called spin eigenfunctions that are eigenfunctions of the total spin operator. Yeah, so do not look at a picture like this and say this is a total spin of 1/2. That is not correct. Yeah? So I wanted to have some awareness of that. So now we go to a little bit into the electronic structure of atoms and ions. And now for atoms and ions, the way to talk about, and the way to think about them, the many particle states that can form are the so-called atomic Russell-Saunders terms. And such an atomic term symbol is denoted 2s plus 1 as a superscript capital L. Now, 2s plus 1, that is important, that is called the multiplicity of the state. Yeah, so s is the total spin quantum number. So 2s plus 1 is the spin multiplicity of that state. And capital L, that is the total angular momentum quantum number of that state. As you know, that one electron orbitals, they come with an angular momentum quantum number, which is 0 for an s orbital, which is 1 for p orbitals, which is 2 for d orbitals, 3 for f, and so on and so forth. And just as we have discussed for the total spin, the total angular momentum of a state is also constructed by the individual angular momentum of the orbitals that are being occupied. Yeah, and so just as there are states of total spin S, there are states of total angular momentum L. Yeah, and an L term is 2L plus 1-fold degenerate. That means the total degeneracy of Russell-Saunders terms is 2S plus 1 times 2L plus 1. Yeah? Now, from atomic spectroscopy of ancient days, L equals 0, 1, 2, 3, 4 are given the symbols S, P, D, F, G. Yeah? Now, there are the Hund's rules, and the Hund's rules tell you, Hund's first rules tell you that terms of a given configuration with a higher S are lower in energy. Yeah? And for terms with a given configuration and equal total spin, the higher total angular momentum is lower energy. These are the two Hund's rules, and they're reflected very well in tables of atomic spectra. Now, you will need all of this because ultimately we will think transition metal chemistry in terms of the individual ions that carry a given number of d electrons. So now let's look at the simplest case here. So we have 5 d orbitals here, and we have 1 electron that occupies them. So in terms of the total spin, we have 2s plus 1 equals 2, because the total spin must be 1/2. Now we have 5 equivalent ways to put that 1 electron into the 5 degenerate orbitals, and hence the total angular momentum L must be 2. And so that here defines a doublet D state. Another simple case is if we have 1 electron in each of these orbitals, and so our total multiplicity is 6, 2s plus 1 equals 6, because s equals 5/2, yeah? And that is due to the fact that m sub s equals s here, and that is 5/2. Obviously, that is the only way to put 5 electrons with parallel spin into those 5 orbitals. Hence, that state is non-degenerate with respect to the orbital angular momentum, and the Russell-Saunders terms must be sextet S. That would be the case for manganese 2 or iron 3, which are therefore called the sextet S ions. Yeah? So sometimes when you read a paper on manganese 2 or iron 3, they will talk about sextet S ions. And that is the reason for that the parent atomic Russell-Saunders terms is sextet S. Now, for partially occupied D shells, it's getting more complicated. Now, look at that situation. Even if, like, the spin is simple, you have 2 parallel spin electrons. That would give you a spin triplet, so 2s plus 1 equals 3. But now, if you count it through, there are 10 ways to put these 2 electrons with parallel spin in 5 orbitals. And if you work out through the procedures to determine Russell-Saunders terms, I think you have suffered through that in your PChem lectures probably at one point or another. Otherwise, you can, of course, read any book on atomic spectroscopy that will tell you the procedure how to determine that there is arising a triplet F and a triplet P term from that. Yeah, so these are Russell-Saunders terms. And they are of distinct energy, and they do show up in the atomic spectra. So even if you don't like it, you can't avoid it, because like when you do an actual experiment, that's what you measure. So it is unfortunate that these things are so complicated, but that's just how complicated the world happens to be. Yeah? Now, for molecules, of course, the symmetry is not spherical as for an atom or an ion. And there, the total angular momentum is no longer a good quantum number. So what we say that is in a molecule, the angular momentum is quenched. It is not completely quenched, and I think in your lectures on EPR, you may hear that like a little bit of angular momentum is being reintroduced. But for the moment, let's just say the angular momentum is quenched by a non-spherical symmetry. But then what takes the role of that is the total symmetry of the molecule. And I assume that the majority of you have heard a course on group theory, where you in detail and systematically learn how to classify the symmetry operations of a given system. So you can classify a molecule according to a given point group, and that point group contains symmetry operations like rotations, improper rotations, inversions, and reflections. And as you know, if you work that out, then each point group has a number of irreducible representations, and that you can think about that as a symmetry quantum number. Now, in order to not get confused, I strongly recommend to follow a consistent and logical notation, and that is by using small letters to talk about orbitals, one electron level, and capital letters to talk about states, so many electron levels, because obviously your orbitals have symmetry and they will transform according to the irreducible representations of the point group, as is the case for the many particle states. Now, obviously, we cannot cover a whole course of group theory here like in 20 minutes, and I'm not trying, I will not even start to attempt it. Just say for what follows, it's important that you know that a T label, so capital T or lowercase t, refers to a triply degenerate level. A capital E or lowercase e refers to a doubly degenerate level, and A and B's are non-degenerate levels. So the role of the Russell sound as term symbol when it comes to classifying molecular many-particle states is 2s plus 1 gamma. So 2s plus 1, again, is its total spin multiplicity, and capital gamma is the irreducible representation that the total many-particle state is transforming to. Now, that was already a lot of pretty formal theory, so now we take it a bit easy and look at the foundations of ligand field theory, and then you will see that all of these things I've been talking about, unfortunately, like piece by piece, will like sneak into the discussion that we have on coordination chemistry. So now let's be really simple and ask ourselves, so how do we make a bond between a metal and a ligand? And so you will realize that the transition metal is either truly positively charged or at least partially positively charged. And the ligands that attach to these transition metal ions are either negatively charged or partially negatively charged. So there is an electrostatic attraction between them. And that is already the driving force for really forming coordination compounds. We will go into a bit more detail a little later. So look, for example, at this simple ligand here. That's ethylene diamine, and it contains two NH2 groups. These NH2 groups have lone pairs here that are attached to the nitrogens. And if you look at the electrostatic potential, there's negative electrostatic potentials in the region of these lone pairs. And so there is a driving force of attaching these lone pairs to the positively charged metals. Now, in terms of proteins, it is absolutely stunning how much chemistry a protein can do with a very, very restricted set of ligands at its disposal. As we know, there are few external ligands that come into bioinorganic chemistry, but in terms of, if you look at this through the eyes of a coordination chemist, it is absolutely amazing, like how little variety nature has to create all that amazing functionality of metalloenzymes. Now, in terms of protein-derived ligands, we have nitrogen-based ligands, and that is, of course, here imidazole rings of histidines. And in already very rare cases, it would be the NH2 group of a lysine. So nitrite reductase would be one of the cytochrome C nitrite reductase, one of the very few enzymes where lysine coordinates to a transition metal. In terms of oxygen-derived ligands, it would be a phenolate ligand from a tyrosine side chain, carboxylates from glutamate or aspartate, and in very rare cases, it would be an alcohol group, like an OH group from a serine. Then there is sulfur, and in sulfur, it is mostly cysteinate so thiolate groups from a cysteine side chain, or a thioether from a methionine. And that's already it. And that is enough to do basically any chemistry you ever have heard of. And so much chemistry chemists would love to do in the lab and are not able to do it. And that is fantastic and it's marvelous. And of course, it's like the big dream of bioinorganic chemistry to disentangle. How does nature do that with so little flexibility in the chemistry to create so much function? Yeah? And for that, you need to dig deep into the electronic structure. And for that, you have to put up with all the nonsense that I've been talking about earlier. Yeah? Good. So, complex geometries. So obviously, the coordination number is the number of ligands around a given metal ion. So if the coordination number is 3, possible geometries around the metal are trigonal or trigonal pyramidal or T-shaped. For coordination number 4, complexes can be quadratic planar or tetrahedral. For coordination number 5, they can be quadratic pyramidal or trigonal bipyramidal. For coordination number 6, compounds are dominantly octahedral. These are limiting geometries. They belong to given point groups. Of course, in an enzyme, you always have lower symmetry, but it's super useful to take a step back and not say biology is always without any symmetry. There is an approximate symmetry, and that approximate symmetry, A, has functional relevance, and B, is being reflected in the spectroscopic and other physical properties of those metal ions. So let's look at iron, for example. You have tetrahedral iron sites, as in rubridoxin. So that is approximately tetrahedral. It's, of course, not perfectly tetrahedral just because of these carbons here on the silates. And, of course, there are distortions on these angles that are slight deviations from tetrahedral. But by and large, these things behave like tetrahedral iron plus something that you can figure out. Yeah? Now, trigonal bipyramidal site would be met in 3,4 protocategoid dioxygenase. So with a little bit of imagination, you will see a trigonal plane here spanned by that phenolate, that imidazole, and an OH group, and then you have a long axis here from the second tyrosine and another imidazole. Tetragonal pyramidal is an important geometry because there is an open coordination site, and tyrosine hydroxylase would be one of those examples. And there are tons and tons and tons of octahedral metal sites, and here I've just shown you lipoxygenase, which happens to be one of them. So there is that coordination geometry. It is approximate in enzyme active sites, but it's important. So now let's go a bit deeper beyond the surface and look into the electronic structure. I already talked a lot about these metal d orbitals, and if you plot them, these are the shapes. I'm sure you have seen them many times. So let's draw coordinate axes x, y, and z. And so what we're plotting here are isosurfaces. So that means values, the same value of a given function. Say 0.03 would be a typical value. And then red would refer to positive values of that function, and yellow would refer to negative values of this function. Now, it is important to understand that all of these orbitals carry a sign with them that is physically irrelevant. So you could multiply all of this by -1 and turn red into yellow and yellow into red, and that would not change the physical properties. But what does matter is the number of nodes. So here is a node where the function value is 0, and it matters where these lobes of these functions are located. Because in terms of the interpretation of these functions in quantum mechanics, it is the square of the function that is related or proportional to the probability of finding the electron in the space that is occupied by these lobes. So that means, think about like squaring the thing. It will look still similar, but the sign will disappear. You will see that if an electron occupies such a dz squared minus r squared orbital, it will primarily be located along the z-axis with a donut probability in the xy plane. So in the dxz orbital, the probability is located between the coordinate axes, so you will never meet the electron directly on the z-axis or the x-axis or the y-axis, but it has its probability located between those coordinate axes. Yeah, similar for the dyz, that is like related by just a rotation to the dxz, and similar for the dxy orbital, that's also related by another 90-degree rotation. Now, if you take this orbital and rotate it by 45 degrees, you end up with the dx squared minus y squared orbital that's similar as the dz squared orbital, has its probability amplitude on the coordinate axis. So you call about probability amplitude is the value of an orbital. So that is basically the unit of such an orbital is probability amplitude. And it turns into probability when you square it. So that is... So it's actually probability density. Yeah, so probability per unit volume. So now what happens now if you take such a transition metal ion and put it into a ligand field? And now here we take the point of view of the founding fathers of ligand field theory, and it's not hard to figure out that these were definitely physicists. And as you know, physicists don't like chemistry very much, and they find all this very strange with like what is a lone pair, or what is an amine, and what is a halide, or so. They find that all very weird. But what they do know, and what they do want to think about, is negative charge that is on the ligand, or partial negative charge. So the abstract way of thinking about it that these people had, where that they sit like on the center of the transition metal, and they see the ligands as a field of negative point charges. Yeah, so that is the abstract model that defines ligand field theory. Now let's look at the very simplest possible case that there is a ligand field of octahedral symmetry. Yeah, so we have 6 of those ligands. They sit on the plus minus z axis, plus minus x axis, plus minus y axis. Now, and here's just a plausibility argument. If you would be an electron, you're negatively charged. And so you would obviously be repelled by the negative charge on the ligand. Now, if you're sitting in the dz squared orbital, your average distance from this unpleasant negative charge that surrounds you would, on average, be shorter than the distance you would have if you would sit in a dxy or dxz orbital. Okay, when you work through the mathematics, this is basically how it plays out. And that means that ligand field is creating a splitting, energetic splitting of these d orbitals. Now, in an octahedral field, the way it turns out is that these orbitals split into a T to G set that contains the dxy orbitals, dxz and dyz, and an EG set according to the irreducible representations of the octahedral group OH that contains dx squared minus y squared and dz squared. So now we have to fill in electrons. So in the free ion, we had the 5 d orbitals degenerate, and with 1 electron in them, we had a doublet d state. Now, if we take these electrons, this 1 electron, and put it into the compound, which is in an octahedral ligand field, it would go into one of these T2G orbitals, and that would create then a doublet T2G state. Note again, there's lowercase symbols for the orbitals, there's uppercase symbols for the many particle quantities. Yeah, so that creates the doublet T2G ground state of a D1 system. Okay, very importantly is to note that the interaction with the ligands destabilizes all of these d orbitals, and actually this is drawn totally out of proportion. If you work through the numbers, then the destabilization of these d orbitals is, say, in cucumber units is 200, and the splitting is 0.1 or so, yeah? So we're talking about a small splitting that is induced by the ligand fields on top of a huge destabilization by the negative charge. Now, I don't want to work through the mathematics here, but in principle, all of the mathematics of ligand field theory fits onto one page. and it's here, and it's in your lecture notes. You're welcome to work through it. But what you absolutely should not do is like to work through that mathematics and then say, ha, I have an expression for my ligand field splitting, so that is this here, the energy difference between the T2G and the EG orbitals, and it's being defined as 10 dq. That is simply a definition. Don't ask why this is so. It's simply defined as 10 dq. And there is a mathematical expression for it, which is 5/3. Q now is the charge on the ligand. R to the 5th is the metal ligand distance. And then the expectation value of the radial wave function over the operator R to the 4th. Now, if you put in like reasonable d orbitals, evaluate that integral, put a reasonable metal ligand distance, you end up with ligand field splittings that are total bogus. Yeah? It's really not what you should do. It's not what you should want. This is not an ab initio theory. This is a model. And that's why I talked to you about it so much in the beginning. So the feature that ligand field theory gets right is that there is that splitting between those orbitals. The physical origin to which it attributes that splitting is wrong. Yeah? So this is how it works. It's also important to understand one thing. If you make such a simple model, your goal is to create insight, pictures that you can use. Now, if you take a simple model and mathematically over-elaborate it, it's defeating the purpose. So if you see papers on ligand field theory that contains more equations than words, it's very likely useless, and you don't need to read it because it is not achieving what it set out to achieve, which is to give you insight. So now, if you have that ligand field splitting, how do you measure it? And you can measure it with optical spectroscopy. Now, obviously, if you have such a D1 system here, and ground state is doublet T2G, one electron in this T2G shell, now you shine light on it, and the frequency of that light equals the energy splitting between these orbitals. Then you get a resonance, and you promote that electron to an excited state in which that electron occupies the EG, one of those EG orbitals. Yeah, and this is pretty much what happens. I say only pretty much. This is not exactly what happens, but this is pretty much what happens. And here you have an example. It would be hex-aquo titanium 3+. It's a D1 system. And if you shine light on it, you will find a resonance on the order of 20,000 wave numbers. Now, this absorption band is unsymmetric, and we will later learn why it's unsymmetric. But let's be a bit abstract for the moment and say we have an experiment, and that experiment measures me my ligand field splitting. Now, if you're a chemist, you say that's great, and now you want to go out in the world and want to make it systematic. So you want to try many different ligands and test their ability to create such a ligand field splitting. And hence, what you come up with is the so-called spectrochemical series. So this is something that people did in the 1950s and 60s. And so they ordered like many, many different ligands that you meet in coordination chemistry according to their ability to split those metal d orbitals. So a spectrochemical series would look like this. So at small delta, so it's small 10 dq, small ligand field splitting, you would have ligands like iodide or sulfide, fluoride, OH-, and then in the middle you have ligands like H2O and NH3 and perhaps nitride, and on the very right-hand side you have those ligands that lead to huge ligand field splittings. That would be ligands like CO or NO and very extreme NO+. You say, okay, that's nice, and then you look at it for a bit and you say, well, but there's something fishy here, yeah? So if I have a model that tells me that the splitting is of electrostatic origin, and it's proportional to the negative charge on the ligand, then it's really strange that OH- would lead to a smaller ligand field than H2O, isn't it? That already tells you that you should be a bit suspicious about the origin of the ligand field splitting according to ligand field theory. We will later see why this is so. In terms of biochemistry, Andy Thompson a while ago had suggested a biochemical spectrochemical series where the weak field ligands would be carboxylates as aspartate and glutamate, a bit weaker than cysteine, weaker than tyrosine, weaker than methionine, and then on the higher end would be histidine, lysine, and histidinate. But there are no real intrinsic, very strong field ligand in biology. You have, of course, in hydrogenases, for example, strong field ligands like cyanide and CO, but the protein itself only provides moderate to weak field ligands. It's also part of the way that biology chooses to work. Now you have that, and now we see one of the major triumphs of ligand field theory, and that is the so-called ligand field stabilization energy. The idea is the following. So relative to the free ion, once you form a ligand field, all of the d orbitals are destabilized. But relative to the center of gravity of these d orbitals, the T2g orbitals are destabilized and the EG orbitals, stabilized, whereas the EG orbitals are destabilized. Yep. So if you put numbers on it, then relative to the center of gravity, the T2g orbitals are minus 2 over 5 delta, where delta is the ligand field splitting stabilized. The EG orbital 3 over 5 destabilized. Now we put electrons in one after the other. And so you would see that, like with one electron, my ligand field stabilization energy would be minus 2 over 5 delta. For 2 electrons, it's minus 4 over 5 delta. For 3 electrons, it's minus 6 over 5 delta. Now the fourth electron would have to enter here. Yeah, so first 3 electrons enter here, here, and here. Fourth electron would enter here. And that would subtract from the ligand field stabilization energy to get minus 3/5 over delta. And at the fifth electron that would go here, the ligand field stabilization energy would be 0. And then for the second set of 5d electrons, it would go the same. Now, what does that mean? What we have here in the open circles are hydration energies of hex-aquo transition metal 2+ ion. So what is that? It's basically the energy that is being released if you bring together in the gas phase a metal 2+ ions and 6 water molecules to form the complex. Yeah, basically speaking, that's it. And so what people have measured is this like very funny double bowl-shaped curve. Now, I think you would be very tempted if you're like a PhD student to like take this set of data and fit a straight line through it, wouldn't you? Then Then you would go to your advisor and your advisor says, it doesn't look that good. Repeat. Then you would repeat, and then it would still look funny. And then he said, repeat until like either you quit or the advisor is satisfied. And then it looks like this funny double bowl-shaped thing, and there is no escape. It's real. Data is irregular. Now, at that point, people thought, so we have that ligand field theory thingy, and now we have measured like the 10dQs, those deltas, from optical spectroscopy. So we have a spectroscopic measurement of that delta, and if that concept of a ligand field stabilization energy is any meaningful, what I should do is to subtract that ligand field stabilization energy from this double bowl-shaped thing, and then I end up, indeed, with a straight line, and you do. So you take a spectroscopic quantity, the measured delta, you subtract it from these thermodynamic data here, the hydration energies, you end up with a straight line. So what is that straight line now telling you? That straight line is telling you that like the binding energy of a water molecule to a transition metal is increasing as you go from the left to the right on the series. And why is that so? That is so because for each additional element you add a proton and an electron. So a proton is a positive charge. Now the additional electron will start to shield that positive charge from the proton, but it will not shield it completely. That means as you go from the left to the right of the transition series, it's more and more of the nuclear charge is shining through, so to say, and is seen by those water molecules, which are hence more strongly attracted. So it's the effective nuclear charge that gives you the trend in that data, And it's a ligand field stabilization energy that gives you that funny double bowl type behavior. So that was a major triumph when ligand field theory was able to explain this set of data. And it explains many, many, many more things. And before we get into that, what we need to look at is, so far we have talked about the ligand field as if there would be only one electron. And I've been very careful in the beginning of this lecture to tell you that one electron is not what you have in reality. You have many electrons. And whether we like it or not, these electrons repel each other. Now, when it comes down to it, quantum chemistry since 1928 is basically an uphill battle against the consequences of electron-electron repulsion. And you hear a lot more about that in the next lecture that we do after the break. Now, in ligand field theory, it turns out that electron-electron repulsion is really simple because it can be described by a single empirical parameter. Now, let's talk about qualitatively what's happening. Now, the strongest repulsion between two electrons that you can have is when two electrons occupy the same orbital with anti-parallel spin. And that repulsion is a fair bit larger than the repulsion that you get if you have two electrons with opposite spin in different orbitals. And that repulsion, again, is a fair bit, is actually very much stronger than the repulsion that you have for two electrons in different orbitals but with the same spin. And the difference between this situation and that situation, that is called the so-called Fermi correlation. Yeah, that is that electrons of the same spin repel each other less strongly. So there is a so-called Fermi hole in the electronic structure that is basically caused by the anti-symmetry of the total wave function, and before it starts to sound like gibberish, I stop here because I will talk more about it in the next lecture. For the moment, just take it for granted that if two electrons have the same spin, they repel each other a fair bit less strongly than if they have opposite spin. Yeah? Now, the consequences of that is that in degenerate orbitals, electrons will first enter with the same spin in different orbitals, and that is already enough to explain Hund's rules in atoms that I talked about in the beginning. But if you accept that this is real, that means each configuration, distribution of electrons among orbitals, produces several states that have different energies. And as I said, in ligand field theory, there is a single parameter that is called B, that is so-called the Raka B parameter, that has a value on the order of 1,000 wave numbers, that takes care of all the complexities of that electron-electron repulsion. Now let's look at one example. For here in the D2 configuration, you would have a state where you have like two electrons in the T2G shell. You would have a state that's singlet T2G that essentially consists of two electrons occupying the same orbitals, and a triplet T1G state that consists of electrons with the same spin occupying different orbitals. Now, if you work through the mathematics of ligand field theory, you will find that these two states are split by the amount of 4B, and so that is on the order of 3 to 4,000 wave numbers. So that is it's the same electron configuration. Yeah? Two electrons in the T2G shell produces two states that are split by 3 to 4,000 wave numbers. You go to your spectrometer, you put light in with a frequency of 3 to 4,000 wave numbers, you will get a peak because these states are real. Now, if you don't acknowledge that that you are measuring many electron states, you will not predict that. Yeah. So if you go to your, say, DFT program or your DFT aficionado or your like solid state theoretical physicist, they will not predict these energy splittings, and hence they will not be able to interpret the experiment correctly. That is an example of so-called multiplet splitting. And transition metal chemistry is littered, is full of these multiplet splittings, and you need to have at least a basic appreciation that these things are there. Really, to play piano of it will require a few years of study, I'm afraid, but it's worth it. You understand a lot more about transition metal chemistry and spectroscopy if you put in the time to study that. Now, one other consequence of this is that there are high and low spin complexes. So now we talked about the ligand field splitting, the ligand field stabilization energy, and we talked about the electron-electron repulsion. So let's look at the D5 configuration, for example, where you would have one possibility is that minimizes the electron-electron repulsion is to have all electrons with the same spin occupying these 5d orbitals. Alternatively, but then of course you're sacrificing ligand field stabilization energy because you put these two electrons in like higher lying orbitals. Now for low spin configuration, you would obviously gain ligand field stabilization energy, but you would have increased electron repulsion. So what wins? And what wins obviously depends on how much ligand field stabilization energy is there and how much electron-electron repulsion is there. Now, since the electron-electron repulsion is basically a given, it depends on the ligand field. It depends on the chemical nature of the ligand. Yeah? And so you can measure it by the value of the ligand field splitting delta divided by the electron repulsion parameter B. Yeah? So if that is small, you have a so-called weak field ligand, and then the ground state of your system would be a high spin complex. If that splitting is large, say on the order of 20 to 30, you would have a strong field ligand that would happen, say, with CO or cyanide and these ligands, and then you form a low spin ground state. Obviously, there must be a critical value of delta over beta where it's just enough to drive it between high and low spin. That leads you to the entire large research field of spin crossover compound that are just very close to this to the crossover point between high spin and low spin. So, where we are now is at the place where we can summarize all of the information content of ligand field theory in one set of diagrams. These one set of diagrams are very famous. They're called Tanabe-Sugano diagrams, and each and every textbook on inorganic chemistry has printed them in the appendices. From what I've told you so far, you'll be able to understand what these Tanabe-Sugano diagrams want to tell you. So, let's look at the Tanabe-Sugano diagram. Tanabe-Sugano diagram on the x-axis has the ligand field splitting parameter delta in units of the RACA-B parameter, so in units of the electron-electron repulsion. Now, and on the y-axis, you have the energy of each of these multiplets that you can form in a given Dn configuration relative to the ground state, again in units of the electron-electron repulsion. Now, at the origin here, you have ligand field strength of 0, so that means what you have here is the spectrum of the free ions. So what you have here on the y-axis, on the origin, are all of the Russell-Saunders terms that you can form for the Dn ion in the free ion limit. As you turn on the ligand field, you first have a weak field situation, and you will see a few of such diagrams in a moment. And then you will see how these states, these many electron states, these Russell-Saunders terms of the free ion will evolve and correlate to many particle terms of the molecular compound. And obviously, a Tanabe-Sugano diagram in general will have two domains. The weak field domain, where you have a high spin ground state, and then there is a critical ligand field strength at which the ground state becomes a low spin state. And then you have a strong field situation. The Tanabe-Sugano diagrams look discontinuous there. Yeah? And what will happen now is that you can see the splitting of the free ion terms into molecular terms as a function of ligand field strength. And that is an invaluable guide to transition metal spectroscopy. Now, look, for example, here at the D2 ion, and we have on the x-axis here the ligand field splitting parameter delta, and here we have all of the terms that arise on the free ion in the D2 case. So we would have a triplet F ground state, then you would have a singlet D, a triplet P, a singlet G, and a singlet S. Yeah? Now we have an octahedral field here, and let's look at the D2 state. So we have 2 electrons here in the T2G shell, and from what I said, they will have, in the ground state configuration, they will have the same spin, so that's a triplet state, and if you work yourself through the mathematics of your group theory, you will find that this configuration here is triplet T1. Now, when you measure a spectrum of a D2 system, such as the vanadium hex-aquo 3+ complex, you will find that it has 2 bands in the visible region. Now, you go to your Tanabe-Sugano diagram and you understand what that is. Now, from your selection rules for optical spectroscopy, you will know that optical transitions are only allowed if the total spin of the system does not change during the transition. So you have a triplet ground state, hence you go through all of these terms here in the Tanabe-Sugano diagram and ask yourself which are the ones of triplet spin symmetry, like triplet multiplicity. And you will find a triplet T2 and a triplet T1 state, and so you can basically immediately assign these 2 absorption bands to a triplet T1 to triplet T2 excitation here, and a triplet T1 to triplet T1 excitation here. That's fantastic, and there are hundreds and thousands of such of examples of that show you that the Tanabe-Sugano diagrams are right. So that means ligand field theory has taught you something fundamental about the properties of transition metal ions in DN configurations. It makes you believe that all of these things make a whole lot of sense. Now, let's see, what are these like T2 and T1 states? So you see that their energy rises as you increase the ligand field strength. And that makes sense because they correspond to T2G to EG excitations. Yeah? And as you increase the ligand field strength, these splitting becomes larger, and hence the energy of the triplet T2 and the triplet T1 goes up. There actually is a third state, a triplet A2, that in principle you could see, but it's very high up in energy. It will usually be like there or there or there or somewhere out there. Yeah? Now, it is also interesting to note that you will have a few states here, a singlet T2 and a singlet E, that basically do not depend on the ligand field strength. So what states are those? Those states are states that are formed by spin flips inside the T2G shell. Yeah, so they only depend on the electron-electron repulsion, and they will be totally insensitive to the ligand field because electrons that are sitting here in the T2G shell, they don't care about EG orbitals that are here, 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 or here, or there, or wherever. Yeah, so you see how much insight you can get from these Tanabe-Sugano diagrams. They're your best friend as an inorganic spectroscopist. And they can get fairly complicated. So if you have like the Tanabe-Sugano diagrams for D6 ions, you will see that there is a very rich atomic spectrum here on the x-axis that resolves into many, many, many molecular terms here. And here you see what I've talked about. In the D6 case, there is a high to low spin transition. Yeah? And on the high spin side, you have a quintet T2 ground state. On the low spin side, you have a singlet A1 ground state. And it is iron 2, the best studied example, and it leads you to that vast field of spin crossover chemistry that can be done with iron 2. Now, if you have spectra of iron 2, you will find, and we go into that later, that on the high spin side, so that is hex-aquo-ferrous ion, you will typically find a band centered around 10,000 and split by around 2,000 wave numbers. And that comes from these T2, quintet T2 to quintet E transitions. So if you work yourself through all of that stuff, you will find that there is only one other quintet term here, and that is the quintet E. That is basically the 6 electrons being excited from the T2G to the EG shell. Now, a peculiar case is met in the D5 configuration. Now, in the D5 configuration, as I said, is sextet S ions. And from what I said before, there only is a single sextet configuration that you can reach by distributing these 5d electrons, these 5 electrons on these 5d orbitals, and have maximum spin. And that means on the weak field side of the Tanabe-Sugano diagram for D5, you have a sextet A1G ground state. Yeah, that correlates with the sextet S state of the free ion. Now, obviously, it is impossible to excite any one of these electrons to another orbital without changing its spin, because that would violate the Pauli principle. That means all D2D excitations are spin forbidden. And that means you understand why complexes of manganese 2 are usually colorless, yeah, because there are no allowed D2D excitations. Now, compounds of iron 3, high-spin iron 3, are usually not colorless. But that is not due to D2D excitations, but ligand-to-metal charge transfer excitations that are not part of ligand field theory. So here you would step outside the ligand field theory model if you want to interpret those. Yeah? But if you if you're careful, and this here is a very historic spectrum that was measured by Klicksbühl-Jørgensen, and it's actually these dots here, they mean something. He measured it like point by point. This is like how 19 Dickety-Duck you measured absorption spectra, you measured them point by point. And Klicksbühl-Jørgensen, who basically was one of the founding fathers of ligand field theory, he even was reported to rather look at columns of numbers and rather than at a spectrum. Anyways, so all of these absorption bands for hexaquomanganese 2 are extremely weak. So you see the molar extinction coefficient is 0.03. Yeah, it's extremely weak bands. They must be spin-forbidden excitations, and if you go to the Tanabe-Sugano diagram, you can immediately assign all of them. You look at the terms of quartet symmetry, you will find quartet T1 here, quartet T2 here, quartet A1 and quartet E here, quartet E here, quartet A2 here. It's really fantastic how simply and comprehensively you can map these spectra on the basis of ligand field theory. It will also explain to you why this band is sharp and these are broad. All of these bands belong to either an excitation or a de-excitation from a d electron. So they will slightly change the bonding in the compound, whereas these excitations here, they are spin flips. So electrons simply switching spin inside a given orbital where you don't change the bonding, and hence you get very, very sharp absorption features. So that is all very sweet. And it explains a library full of experimental data that has been obtained on transition metal compounds. So now we want to elaborate a little bit on that and eventually bring it to the point where I hope to demonstrate to you that it's also useful in biochemistry, yeah? That it's not only hex-aquo transition metal compounds that you can apply this model to, but actual real enzymes. But before we do that, we need to bring up one subject, and that is the Jahn-Teller effect. The Jahn-Teller effect tells you the following. We have seen that in many of these multiplets that we already ran into, they are degenerate, so they are of E or T symmetry. And they arise from situations in which an electron can occupy any one out of a couple of degenerate orbitals. For example, for the low-spin D7 configurations, you would have a fully occupied T2 shell, and there would be one additional electron, and that one additional electron could either go into, say, the x squared minus y squared orbital or the z squared orbital. Now, the Jahn-Teller theory tells you that there will always be a nuclear motion that spontaneously occurs that removes the degeneracy and forces the system into an orbitally non-degenerate state. Now, that spontaneous distortion could be either an elongation of the octahedron that would stabilize the z-squared orbital relative to the x squared minus y squared orbitals, and the electron would go there in the electronic ground state, or a compression which would destabilize the dz squared orbital, and then the electron would go into the dx squared minus y squared. The Jahn-Teller theorem will not tell you in which direction a given system will distort. It will simply state that some form some sort of distortion will occur to lift that degeneracy. It could also be, say, a trigonal distortion or some other kind of distortion. It will not tell you what is happening, but it tells you that something will happen. It is actually quite interesting to dig out the original paper by Jan and Teller, because you expect like an enormously elaborate mathematical construct that proves in great generality the statement. But that's not the case. What they have done, they have basically worked themselves through all of the possible point groups one by one and found that what they suspected, that such a distortion will occur, will always be true. For linear molecules, there is something related that's called the Renner-Teller effect, but we're basically not dealing with linear molecules. And the Jan-Teller effect is an important aspect of coordination geometry. Yeah? Now, we're revisiting now our hex-aquo-titanium 3+ compound that we've met in the beginning, and you will now understand that the doublet T2G ground state is Jan-Teller active. It will split, and the EG, doublet EG excited state, is also Jan-Teller active and will split. So that relatively simple case of a doublet T2G to doublet EG transition that we met in order to introduce a ligand field splitting, in reality is a fairly complicated problem where both the ground state and the excited state are Jan-Teller active. Now, I don't want to dwell on that too much, but saying that it's a ground state Jan-Teller effect is always is weak, not always, but is weaker than the excited state. So a Jan-Teller effect that comes from a partially occupied T2G shell is always weaker than the Jan-Teller effect arising from a partially occupied EG shell. So that splitting, what you see here in the optical spectrum of the hex-aquo-titanium 3 compound, is essentially the Jan-Teller effect in the excited state that you see here. Yeah? And so you understand now why that band splits into two. That's nice. So now let's go one step further. And I've told you that these transition metal compounds, they can exist in many different coordination geometries, also in enzymes. And now it starts to be useful because you may want like to deduce the effective coordination geometry from your spectroscopy. And for that, we need to understand how the d orbital splittings vary as a function of coordination geometry. So far, we spent all our time on the octahedral case, where the splitting of the d orbitals is into a T2G set and an EG set. Now, remove one ligand from the z-axis, and you will find that the z squared orbital is stabilized, as is the xz and yz orbital. So that means the tetragonal pyramid will have this type of ligand field splitting, where the lowest orbitals are xz and yz, then followed by x, y, z squared, and x squared minus y squared. Now remove the second ligand here from the minus z-axis, you come to a square planar compound. Then the by far highest energy orbital in the d set is the dx squared minus y squared orbital. And then the z squared and xy orbitals, depending on the compound, can be either in this configuration or interchanged, and then at lower energy you would have xz and yz. For trigonal bipyramid, you will find a completely different ligand field splitting, where the pattern is 2 and 2 and 1. So the highest, by far highest orbital in the trigonal bipyramid is the dz squared orbital, and then you have the xz, yz, and xy, x squared minus y squared orbitals that form degenerate sets of e orbitals. Now, for the tetrahedral case, you have the exact opposite splitting pattern as in the octahedral case. So here you have a low-lying E set of orbitals, x squared minus y squared and z squared, and then a higher-lying set of x, y, xz, and yz orbitals. Now, I've drawn this here purposely, that the splitting that you see here in the tetrahedral case is smaller than here in the octahedral case. It is one of the predictions of ligand field theory that the splitting in the tetrahedral case is minus 4/9 that of the octahedral case for ligands of equal strength. That means that in the tetrahedral case, the splitting is by symmetry about a factor of 2 smaller than in the octahedral case. There is a consequence of that. consequence of that is there are no low-spin tetrahedral complexes. Yeah? Tetrahedral coordination compounds are always high-spin. And the reason for that is also explained by ligand field theory. It's very nature that this ligand field splitting is much smaller, so hence you're always in the weak field limit. Now let's move a little bit towards the real world and look at some spectroscopy. That is like now ancient spectroscopy done in the lab of Ed Solomon, and he has been. I didn't mean to sound that wrong. Let's see. This is beautiful spectroscopy that comes from the lab of Ed Solomon. These statements are not mutually exclusive. So these are all actually MCD spectra of high-spin iron II model compounds. That these are MCD spectra is not important in the context. The only reason for that is you can record MCD spectra all the way into the near infrared much easier than absorption spectra. Absorption spectra are complicated by like scattering and so on and so forth. With MCD spectra, you have an easier time. But like you can look at these for the purpose of that discussion, look at these as if they were absorption spectra. Now, if you have an octahedral high-spin iron II compound, you will find the pattern that you have a band centered at 10,000 and then split by about 2,000 wave numbers, and I've explained that to you on the basis of the Tanabe-Sugano diagram. Now, using these orbital splitting patterns that I've introduced to you, you will find that a quadratic pyramid will have a band at 10,000, and then you will have another one at 5,000 wave numbers. For a trigonal bipyramid, you will find one transition at around 7,000 wave numbers, and there should be another one, but that usually falls out of the detection range below 5,000 wave numbers. And for a tetrahedral compound, you will have low energy bands, again, Jahn-Teller split at around 5,000 wave numbers. Now, you can use the insights. So all of this readily follows from ligand field theory. So it's readily interpreted in terms of ligand field theory. And I will give you now one example of how you can use it in a biochemical context. And all of a sudden, it will start to make a lot of sense. And you said that, boy, I've spent already 80 minutes listening to that guy. And I hope that after this example, it became evident why it might have been worth it. Yeah, so the enzyme that I'm bringing to your attention here are so-called Reesky dioxygenases. They are non-heme iron enzymes. They have an active site, so they have a Reesky iron sulfur cluster, and they have an active site that are of the 2-his-1 carboxylate type. Here's a facial triad and an external ligand. So what these things here do is to hydroxylate aromatic compounds, so they catalyze this reaction here. It's obviously a very complicated reaction, and we're just focusing on one aspect here. Now, look at this spectroscopy. Now, you start with the MCD spectrum of the holoenzyme in the absence of substrate. Now, that obviously has a Reesky center that contributes to the MCD spectrum, and you have the active site, high-spin iron II, that also contributes to the MCD spectrum. So here in order to disentangle that, you need a friendly biochemist who prepares a form of the enzyme for you that only has one of those sites. That is not so complicated because you can add any chelating agent like EDTA or, I don't know, cyanide or so, and get the active site out. Then you end up with the MCD spectrum of only the Reesky center. Now you subtract that spectrum from this spectrum, you end up with the MCD spectrum of the active site, and it shows you that there is a band centered around 10,000 split by 2,000. Hence, that thing is 6-coordinate. Yeah, and you see it from all those correlations that I've explained to you on the basis of ligand field theory. Now you add substrate, but not dioxygen to that enzyme, and what happens is the spectrum changes. You do the same thing again. You get the spectrum of the Reesky center, you subtract it, and now this is the spectrum of the active site. So it contains a part that is unreacted resting state enzyme, but now you have two more bands. One here, around 11,000 wave numbers or so, but clearly there is the onset of low energy band at around 6,000. So from that ligand field correlations, you will come to the conclusion that the active site in the presence of substrate has gone 5 coordinates. So there was a 6 coordinate to 5 coordinate transition. And that is a very important information because it makes sense. Now, that is like a mechanistic sketch that is still rough, and it would need a lot more work from a lot more people to like even that out. But the initial stages of the reactions, you have gained some insight. And that insight is the following. So in the resting state, you have a 6 coordinate high spin iron 2 site. That makes sense. It's coordinatively saturated. And part of the reason is you don't want that active site to undergo Fenton chemistry in the absence of substrate. So you don't want it to make hydroxyl radicals and other crazy things that will destroy the protein. So the enzyme protects the active site by having it coordinatively saturated. You bind substrate, the enzyme does something subtle to kick out the 6th ligand, water, and then a coordination site opens up. And that coordination site is opening up because then, you want to bind dioxygen. Dioxygen will bind to the active site when the substrate is around, will form like a hot species. This is all Carson and Marty's game and Mike's game, and like many people have worried about the hot species that do form like between iron and dioxygen. These are oxo compounds, hydroperoxides, peroxides. And there is a follow-up chemistry here that leads to a hot species that eventually does the hydroxylations. I don't want to go into that here now. I only want to show you that you can use what ligand field theory offers you to interpret the spectroscopy of these early stages. What I've just shown you has been found time and again and time and again and time and again in non-heme iron enzymes. It's a general principle of how nature has engineered these non-heme iron active sites to deal with dioxygen chemistry by go from a coordinatively saturated 6 coordinate site to a 5 coordinate site that will then react with dioxygen. Now I think we have a few more minutes and I want to spend those few more minutes to negate everything I've said so far. Yeah. So we want to go beyond ligand field theory. And it was already the founding father of ligand field theory, Kliksbühl-Jørgensen, who said early on, he said, personally, I do not believe much of the electrostatic romantics many of my colleagues talked about. And the electrostatic romantics that I've talked about, that is exactly the ligand field model as I have described it. And I'm not sure how romantic you find it, but it's it is clear that already the person who invented all of this, he understood very clearly that it's not all of the story. And I want to make my argument from an experimentalist point of view. Now, say you're in the lab and you have an EPR spectrometer and you happen to have made copper tetraimidazole 2+, so that is a copper 2 compound, it's a D9 system, and then your EPR spectrum looks like this. I don't know how many of you are very familiar with EPR spectroscopy. It's a quite typical EPR spectrum for a copper 2 compound. It has copper hyperfine structure here. It has an axially symmetric G tensor. All of this is fine. All of this you can understand perfectly well on the basis of ligand field theory. But now there is something here. There is that very beautiful structure like these sharp spikes. Now, if you were in doubt what that is, you would make the compound labeled with N15 imidazole, and you will find that this pattern here is changing. And because what it really is, it's hyperfine coupling of the unpaired electron to the nitrogen nucleus. That, on the other hand, is only possible if the nitrogen nucleus sees some of the electron spin. And that, of course, is only possible if some of the electron spin is delocalized onto that nitrogen ligand. Now look at the ligand field picture. What would ligand field theory tell you about a D9 system? It would tell you that the singly occupied orbital is a dx squared minus y squared orbital, which happens to be a copper orbital, and that's it. there is nothing on these nitrogens because, according to ligand field theory, these are just point charges. So you cannot explain what's happening here. And the historical realization was actually very similar. It just wasn't copper tetraimidazole, it was iridium hexachloride, but the argument runs the exact same way. So that means you need to proceed beyond ligand field theory to understand the finer details of this spectroscopy. And there is no other choice but to include those ligands explicitly. Now, in that theory is, of course, molecular orbital theory. Now, I'm sure every one of you have had some form of molecular orbital theory in their curriculum, so I want to be very brief here. So according to molecular orbital theory, you form a bond. And you form a bond between two constituent orbitals. You can form a homopolar bond between two identical fragments. You will form a bonding orbital that has constructive overlap between the constituent fragment orbitals. And you will have an anti-bonding component that is more destabilized than the bonding component is stabilized. That is the way a homopolar bond works. A heteropolar bond works in the way that you form it between a lower-lying fragment orbital and a higher-lying fragment orbital. Now, the bonding component will be dominantly reflecting the lower-lying fragment orbital. The anti-bonding component will be dominantly reflecting the higher-lying component. You will see from that also here, when you occupy both the bonding and the anti-bonding components completely, no bond will form, and that is called electron pair repulsion because the anti-bonding component is more strongly destabilized. Hence, you can define the bond order of a given bond as 1/2 the number of electrons in the bonding component minus the number of electrons in the anti-bonding component. Yeah. So the type of molecular orbitals that you get then, and they're very pretty to look at, you have either a sigma bond that is like located along the bond direction, or a pi bond. You have non-bonding orbitals that are lone pairs, and then you have pi star anti-bonding orbitals or sigma star anti-bonding orbitals. I'm sure you have looked at that. Now, even when you take already the simplest transition metal compound, say a hexahalide transition metal compound, these orbitals look quite complicated, and it's quite some work to figure out like all of the symmetries and all of the things that can happen. So if you have a hexahalide transition metal compound, the ligand p orbitals already fall in symmetries T1G, T2G, 3 times T1U, T2U, 2 times EG, 2 times A2G. Well, it's work to figure it out. However, I want to make only one important point here, and that is the effective ionization potential, so so-called valence shell ionization potentials of the metal d electrons are lower than those of the ligands. That means you more easily ionize an electron from a metal than you do from a ligand. And that means effectively you have to draw the diagram such that you form a heteropolar bond between the metal and the ligand, where the higher energy component are the metal d orbitals, the lower energy component are the ligand p orbitals. And that means, now if you look at it, you will form, just as in ligand field theory, the metal orbitals will split into essentially metal d-derived molecular orbitals of T2G symmetry and EG symmetry. These will, in generally, be anti-bonding components. Yeah? So, and of course, through the bonding, some of the electron density is transferred from the ligand to the metal. One thing actually is a discussion that also comes up again and again in the literature. You can never think of like a transition metal ion, say in a transition metal with oxidation state 3+, of having a metal that actually has a charge of 3+. That is physically impossible. Every atom in every molecule is close to neutral at the end of the day because everything else is absolutely inconsistent with electrostatics. So these oxidation states that we're talking about, they are constructs that help us to think about it. They do not reflect any realistic positive charge or negative charge that is physically there. Anyways, that's a distraction. So in principle, if we look at these molecular orbital schemes, what we have talked about in ligand field theory is just this aspect of it. Yeah, it's those orbitals that are dominated by the metal d orbitals. Now, if we do that and do some form of reasonable molecular orbital calculation on copper tetraimidazole, we will find that the singly occupied orbital now looks like this. It's a sigma anti-bonding orbital that has nitrogen character here. And exactly how much nitrogen character that is, you can tell from the EPR spectrum because the splittings here are directly proportional to the fractional contribution of the nitrogen to that orbital. Careful, as I said many times before, these orbitals are not physical observables. These things help us to think about it. And so if you think we have measured this orbital with this EPR spectrum, that's not the correct way to think about it. It is a nice way to think about it. There is nothing fundamentally very wrong with it, but you should be aware these orbitals are not observables. But you see that how nicely you can explain now all of the facts, all of that spectroscopy on the basis of MO theory. I need 2 more slides, and then we're taking a half-hour break. And that is to take it one step further. Now you can look at 2 important limiting cases of bonding between a metal and a ligand. So the first would be classical coordination compounds of the Werner type coordination compounds, like iron hexachloride. And so you would see that these EG orbitals are mainly metal d orbitals, and they're sigma anti-bonding with the chlorine p orbitals here. Yeah, so no surprises here. The T2G orbitals, on the other hand, they're pi anti-bonding with the chlorines. Yeah? So you have anti-bonding T2G orbitals, anti-bonding EG orbitals. So chlorine is a weak field ligand. Now, if you go to carbonyl complexes like chromium hexacarbonyl, the EG sets are sigma anti-bonding, as they should be. But if you look at the T2G orbitals, they're now bonding components. And now look carefully. Look at, for example, here. So here you have, say, a DYZ orbital, and that has constructive overlap with a CO pi star orbital. So here is an anti-bonding pi star orbital of the CO that has a bonding interaction with the metal. So that is important because the pi star orbital in CO, of course, is empty. Yeah. So here you have something that is referred to as back bonding, where an empty ligand orbital undergoes an interaction with a filled metal orbital. And so by that interaction, the metal back transfers electron density through the ligand. That's why it's called a back bonding interaction. And it has consequences on the splitting pattern, of course. Now, if we now revisit the spectrochemical series, you will find that in the middle of the spectrochemical series are ligands like NH3 or H2O that can form no pi bonds with the metal. So basically here the T2G orbitals stay where they are, and the splitting is basically the sigma anti-bonding interaction of the ligands with the EG orbitals. Now, if you go to the left of the spectrochemical series, these are ligands that form nice pi bonds with metals. Yeah? So the the ligand field splitting does not correlate with the bond strengths. On the contrary. Yeah? So these pi interactions will destabilize the T2G orbitals and will bring these T2G orbitals effectively closer to the EG orbitals, thus reducing the apparent ligand field splittings. And that explains our puzzle that we had an hour ago. Why OH- looks like a weaker field ligand than H2O. It's because it can make a nice pi bond with the metal, whereas H2O cannot. And it also explains the very strong field nature of these ligands here that are all strong pi acceptor ligands, so pi back bonding ligands, where you have an empty orbital on the ligand that forms a bond with the metal, thereby effectively stabilizing the metal d orbitals and forming a bonding interaction here, whereas here you form an anti-bonding interaction. Yeah? So that effectively increases the ligand field splitting and leads to low spin complexes. Yeah? So now I think that is a good point to take a break before we get into the very serious stuff of many particle wave functions and actual quantum chemical calculations. Thank you very much. Ja, mache ich. Okay, nachher gehe ich hier auf allen Vieren raus.